What was it? Can you remember the lab? That's right, that was it. The chapter that we did on naming ionic compounds, we did that 6 solution lab. You had 6 test tubes on a rack, and you had to determine what was in the 6.
Oh, that was not my favorite.
I remember that one. Yes, we remember that one.
Yeah.
That was the kind of reaction that was happening. What we have is an ionic compound. Remember, ionic compound is positive, negative, and this one is positive, negative. And it's like the double date analogy where the 2 couples will switch partners. The A will go with D. Remember that ionic compounds are always given with the positive ion first, then the negative. So A would go with D because that's positive and that's negative, right? And then C would go with B, and it would be written CB, not BC, not in alphabetical order, but because that's positive, that would be written first and then the B. We know the B was negative from up here. So you want to be on the lookout for double replacement reactions, and the way that you can recognize them is by noticing this. You have, and then we have, really you recognize it because you have 2 compounds, 2 ionic compounds, and they rearrange to make 2 new compounds. And really all you have to do is just take the metals and switch places. You did these already. So we have 2 ionic compounds that are dissolved. What am I doing? Not good. 2 dissolved ionic compounds, copper 2 nitrate and sodium hydroxide. I have them both in the plastic containers. I've got, it says 1 capital M of copper nitrate. We're going to learn about what that capital M is later on in the course. That tells us what the concentration of the compound is. And then we have dilute sodium hydroxide. So these are the 2 reactants here. We've got the copper nitrate and the sodium hydroxide. The 2 reactants are going to combine, and they're going to do this double date switch. The copper and the sodium, the 2 metals, are going to switch places. The copper will leave the nitrate and go with the hydroxide. The sodium leaves the hydroxide and goes with the nitrate. Now, what we'll see, and this, try to remember back to that lab that you did, sometimes when you combine ionic compounds with other ionic compounds, nothing happens. And nothing happens sometimes because the products that you get are soluble, and nothing is going to show up. But if something is insoluble, you remember talking about those words when we did that lab? You get solids that show up in some of the combinations, and then not others. And then some of the solids are different colors than others, and that's how we identify what was what. Well, when you combine these, what happens is the sodium with the nitrate, NaNO3, that's a soluble substance, so that just stays dissolved in water. However, the copper, when it leaves and goes with the hydroxide, CuOH taken twice, that's insoluble. Most hydroxide compounds are not soluble. Hydroxide is soluble with sodium, that's why it was aqueous. But when hydroxides are around copper ions, it doesn't dissolve. And you can observe that with this. I have a test tube. I'll put some sodium hydroxide into it. I'm adding the sodium hydroxide first because it's clear, and I'm only going to add a little bit of the copper nitrate because you can tell how dark blue this is. If it's too dark, you can't see through it to see that there's a solid in there. So I'm only going to add a little bit of this one. Just a splash of it. Oh goodness. That's more than I even wanted to add. You see what happened? It makes a solid. It makes an insoluble copper hydroxide. It's nice, pretty blue, solid. It almost looks kind of fuzzy, like there's cotton candy underwater. See, precipitates are nice, Carly. So this is what we see when we have a double replacement reaction. You have ionic compounds that are dissolved in water. You put them together, and if you get a product that's insoluble, then you'll see it. If both of these were soluble, it would just look like still clear. You wouldn't be able to see anything at all. But because we have something that's insoluble, it turned out pretty nice. That's the copper hydroxide. So. Okay, now the term here that we use for double replacement reaction is precipitate. When you get an insoluble compound that forms, one of these two, if it's insoluble, we call that the precipitate. And this clearly, the blue stuff that's formed is the precipitate. I want to show you one other kind of reaction today. And that would be the single replacement. So double replacement, we've got two compounds and they switch places to make two new compounds. That's a double replacement because two compounds are being replaced. I'm going to jump through these to this one. A single replacement, notice the difference, we have an element by itself plus a compound. Instead of two compounds, we have a compound with one element. And the element that's by itself is going to kick one out of the compound, and the one that got kicked out just winds up by itself as an element. So this would be a case of a single replacement reaction. I told you there were 5 types of reactions that you had to know. Double and single replacement are probably the most difficult to recognize. The other 3 are really pretty easy. Just a moment. I have 2 substances. I've got a compound. This would represent the BC term up there. This is copper chloride, CuCl2. When you dissolve copper chloride, it's beautiful. It turns blue. Isn't that nice? And then I have steel wool. You know what steel wool is made of?
Still wool.
It's not made of wool. Wool is taken off of an animal. This is not.
It's a metal.
Yeah, this is mostly iron. We call it steel wool. It's not made of steel at all. Steel is a pretty rust-resistant substance. This is not. This rusts pretty easily. Yep. But anyway, so this is mostly iron. Steel wool is mostly iron. And when I take iron, so iron represents the element that's by itself. That's the iron. And this is the copper chloride. So here's our reactant. Fe, there's our steel wool, and then the CuCl2. Now, notice I dissolved it in water, so this physical state is aqueous. Yeah. A lot of reactions will only occur in water. All right. Well, here's what happens. If I put this steel wool into the copper chloride, it takes a few seconds. A few more than I wish it would. The next single replacement I have to show you is much faster than this. You can kind of see this through the glass. I'm going to bring it around. Whoop. I'm going to bring it around to you. I want you to take a look at what it looks like above the solution and then underneath the solution. Check that out. And when you see it, if I ask you what do you see happening, I'm going to guess that you think of one word. And I'm going to tell you the word is not correct.
You turn the camera on?
No.
See that? See it? It's kind of a reddish color. It's purplish. Let's take a look. See that?
See right through here.
See how it's changing? Oh, there we are.
Zoom in.
Now, does this look like, when I say that this metal is iron, do you think rust? Are you thinking it looks like it's rusting?
Yeah.
Yeah. It looks like rust. It's not though. Because if we look at the pattern for this reaction, what happens, and this really is what happens, the iron, which is the one that was by itself at the beginning, is going to kick the copper out. And the copper winds up by itself. Cu, which is the solid, is by itself now, and then the iron is joining up with the chloride, so it's FeCl2 aqueous. Slowly, the steel wool is dissolving into the substance, and it's going to be dissolved with the chloride. But the copper has come out. So what looks like rust, when you look at this, you think, oh, a reddish, product of iron. It appears to be rust. Really, what is showing up in there is copper. The copper is coming out of the solution and is making copper metal. Now we're familiar with copper in pennies, and wires, things like that. And the copper doesn't look much like copper here, but copper is a reddish metal, like what a penny looks like. That's what this is. This is copper. So single replacement reaction is where metals, depending on how reactive the different metals are, some combinations will make a reaction, some won't. We'll talk more about that on Monday. But this is an example of one that does. This is turns out that the iron is a little more reactive than the copper, and the iron will kick the copper out. The one that's more reactive kicks the other one. All right. The last thing that I have for you is sodium plus water. This is a single replacement reaction as well. Sodium is a metal by itself, and then water, what's going to happen is the sodium can kick the hydrogen out and make hydrogen gas plus sodium oxide, Na2O. Now the hydrogen gas, this reaction turns out to be quite exothermic. And the hydrogen gas, when it's in a very hot environment, does something interesting. And so I want to bring you over here to the fume hood.
They're really nice.
I know it's just about the end of class. I hope I can get this done on time. Okay, I'm going to do it
Oh, you
back
can.
here.
I'm tall.
And I do have to close the hood on this thing because it's pretty deep.
Serena's sitting like a white kid.
Now sodium, we know sodium, you say, oh, sodium is in our food, what the sodium is in French fries, and we have sodium all over the place. And we eat sodium all the time. But sodium as a metal is very, very reactive. It's, hold on one moment. It's pretty soft metal. You can actually cut it with a spatula. Yeah, just cut a piece of it off. Have you seen this before?
If it is what I think it is.
Yeah, well, I think it is. I think it is what you think it is.
it is.
All right. Now, good old water. Water is so harmless to us, right? But if you're a piece of sodium,
Is it going to be really loud? I'm not going to like it.
check this out.
I'm about to
Come
like it.
on.
Oh, it's like swirling around.
See, the sodium's kind of dancing around on the water.
It's going to pop and I'm going to scream. It's falling to death.
If we're lucky, sometimes it's a dud and it just does nothing.
Oh, that's sad.
And what should be happening is it should catch the hydrogen on fire, and the sodium should dance on fire on top of the water.
Wow.
And it's not.
Oh yeah, this is our phlogiston and it's not happening.
And
That's
it's
so
not
sad.
happening at all.
Dead.
Oh, look at it go. Woo! And it's not going to catch fire for us.
It's okay.
Gosh, we'll start with this on Monday.